algebras and the generalized entropy. So take it away.
Cool. Thank you very much for the invitation to speak here. I'm going to be mostly telling you about work that has yet to come out with Jeff Pennington and Edward Witten on some algebraic QFT results pertaining to the generalized entropy of black holes. And if I have time at the end, I'll try to say some words about a paper that's already out on similar ideas applied to de Sitter that's also same authors, but also including Roberto Longo. So the starting point for this talk is just to understand a little bit better what exactly the generalized entropy really corresponds to in Lorentzian signature. Right? So generalized entropy is a kind of a funny object. It's very mysterious because on the one hand, when we talk about the entropy of the matter fields outside of a black hole, this is, in modern terms, we understand this as a von Neumann entropy of some reduced density matrix of the quantum fields. But the area term, at worst, is just some geometric term associated to some, cut of the black hole, like the bifurcation surface. And at best, it's understood as some sort of coarse-grained entropy associated to microstate counting in some UV complete Hilbert space that we don't quite understand yet. Either way, like our present understanding involves two quantities that seem to be on very different footing from the perspective of semi-classical gravity. And the question is whether we can put these on similar footing and get an understanding of the area term within the realm of semi-classical gravity that unifies the way we also understand this von Neumann entropy term. So I'll just start out by describing the setting in which I'm going to be working on. Consider the eternal black hole, and I'm going to restrict myself for this talk to ADS, asymptotics. So consider an eternal black hole that's perturbed by some matter fields. But then perturbed by some matter fields with some order 1 energy, so that there's an analogous, or there's a resulting metric perturbation that's order g Newton, which we can solve for from the semi-classical Einstein equations. And in this setup, the picture that we usually draw for the Penrose diagram looks a bit something like this, where we have some apparent horizon, which is order g Newton separated from the event horizon. And we're going to work in this setup where we're just doing this linear back reaction from the matter fields. But there's a simpler picture we can use for the purposes of what I'm going to talk about, which makes life a little bit easier. So instead of using this more accurate picture, we can always do a gauge fixing transformation, so that because we're working at linear order in the perturbation, we can always do a gauge fixing so that we're essentially on the eternal black hole background, and we just have some matter perturbation that's falling into the black hole. So I'm like, the geometry is the eternal black hole, and then I have some perturbations on top of that, and the metric perturbations are also fields that are going to be propagating on this eternal black hole background. So this is the, roughly speaking, and I'll make this more precise, this is the space of states that we're interested in considering. Okay, so the question is whether there's some sort of Hilbert space understanding that we can get of QFT plus gravity, so semi-classical gravity, where I really mean, when I say gravity, I really mean dynamical gravity. I don't mean QFT on some fixed background. So in that setting, is there some Hilbert space picture we can provide such that the generalized entropy is actually the von Neumann entropy of some density matrix? So not just this thing, but can we get both of these terms to pop out as trace rho log rho of some rho? Okay? Now, this is a question that's been considered before by various people. It was studied classically by Donnelly and Friedel. Jennifer Lin has some papers exploring this in JT Gravity, and Jafris and Kolchmeyer also had a paper in that setting. And there are very subtleties that these approaches run into that are technical and it's not worth getting into right now, but they don't quite seem to get the mark. And my intuition is that this formalism that I'm about to present is better suited for this question, and it's better suited for understanding the Lorentzian physics behind the emergence of the bulk and the generalized entropy. Okay, and one other thing is, so you might say, well, we understand what this thing is in ADS-CFT because we have the Ryuta-Yanagi formula and quantum extremal surface formula and stuff, and we know how to derive that from the Euclidean path integral. But as we know, the Euclidean path integral derivation of this is essentially a more complicated version of the Gibbons-Hawking calculation, and it involves some ingredients which we still don't really understand the interpretation of, like the fact that the thermal circle has to shrink to 0 size in the bulk. Like, why should that? Where does that ingredient come from? It also doesn't quite tell us the structure of the density matrix in semi-classical gravity, from which this area term clearly emerges. So the Lorentzian picture should be able to provide more information on that. Okay, so that's what we're going after. Yes.
When you say we don't really understand this in the Gibbons-Hawking calculation, do you mean that, we understand why the circle shrinks to 0 when you include this particular Euclidean classical solution. Are you arguing that we don't know why we're including it?
Yeah. I certainly don't mean that we don't understand how the calculation goes, but more just why should that be the right ingredient? It gives us the right answer, but we by hand restrict to solutions where that circle shrinks to 0, and we don't really have a more fundamental understanding of that in semi-classical gravity.
What do you mean that we restrict to it?
For example, if you try to do the Lorentzian path integral computation to compute the entropy, that fails because you can't find solutions where the thermal circle shrinks to 0. You just have some cylinder, and the circle will always have some finite size, and then there's no way from that, at least applying the same kind of calculation, you can't land on the generalized entropy. So the Euclidean calculation has this different ingredient that seems to be really important, and we don't really understand where that's coming from a Lorentzian perspective.
Yeah, I think you can just say that it's not manifestly equal to an entropy anymore once you include that, right? It doesn't look like a trace anymore from the bulk point of view, so you have to put in some philosophy about holography or something to convince yourself that you should still include it, which is, I think, correct philosophy. It's just not obvious.
But once you assume that the gravitational path integral computes objects in a theory defined on the boundary, which of course they didn't really understand, but we do.
Yeah,
then it's not so mysterious, right? And it wouldn't make sense to do this particular Euclidean calculation. I would accept, a statement that we don't know exactly what the rules are for what topologies to include, for example, and what not to include. Like the gravitational path integral in general isn't well understood or well defined.
Yeah, I think that's all Venn is saying, is that Euclidean quantum gravity by itself is
it's not a Euclidean versus Lorentzian thing, is what I'm saying.
I think it is. It's like what Daniel was saying. If you try to compute just in gravity, the trace of something, and you follow the natural way you would do that using the Lorentzian path integral, it doesn't seem to land you on the right formula, at least naively. You really need to do this thing where in Euclidean you have you're really computing a trace on the boundary, and then you fill in some manifold in the bulk, but there's no clear interpretation of that as some bulk trace. So how do we?
Yeah, I think this is not really that controversial. He's just saying that using the bulk variables, we can't explain the microstates. If it were manifestly equal to a trace.
But that's not a Euclidean versus Lorentzian.
Well, we can call it path. The words don't really matter.
Well, they do matter because there's some concept to saying that it's a Euclidean versus Lorentzian thing versus bulk versus boundary. Those are totally different things.
If you like, you can say there's a tension between the gravitational path integral, including the sum over topologies, and canonical quantization.
Yeah,
that's the best way to describe the tension.
Yeah.
And we think that the gravitational path integral is better, but that's because we have some holography in mind when we say that, right?
Yeah, because the quantum theory isn't in the bulk.
Yeah, but wouldn't it be nice to have a bulk understanding of the microstates?
Yes.
And that's what he's giving us a step towards that.
Yeah, I definitely won't give you that, but a step towards that.
I said a step.
Yeah, that's true. Okay, so, that's essentially the rough motivation. Any other questions so far? All right. Okay, I'll just leave this up here for now. Oh, that's cool. It just comes down. Okay, so I'm going to use techniques, in order to make progress on this question, I'm going to use techniques from a somewhat recent paper by Edward applying algebraic quantum field theory techniques to semi-classical gravity. So I'm going to spend a bit of time just trying to, just reviewing what that formalism entails and then go back to this setup that I described over there. This formalism is nice because it, at least in the context that we're going to discuss, it uses ADS-CFT in a very, very minimal way, mostly just to put things on slightly firmer footing, but you can really step away from ADS-CFT and talk about asymptotically flat black holes, for example, or de Sitter, so it's a nice formalism for that reason. And a lot of our understanding of holography seems to be tied to the quantum extremal surface, but this formalism, I think, should allow you to move beyond that to more general kinds of surfaces in the bulk. In case you're wondering why I'm going to go through this like very, very formal approach. Okay, so so we're in ADS-CFT, and just to make things concrete, we'll consider n equals 4 super Yang-Mills on the boundary, and we're going to focus on single trace operators on the boundary, as Sam talked about recently. And we're going to consider in particular trace subtracted single trace operators, which, as we know, in the semi-classical limit, because the connected k-point functions decay like 1 over n to the k minus 2, in the large n limit, these single trace operators describe a generalized free field theory, where only the 2-point function is non-trivial and it's order 1, and all the connected higher point functions just go to 0. Let's consider let A be the algebra of operators of these, the algebra of these single trace operators. Okay, so it's the algebra of these W's. And as I said, we're going to consider, let's consider the eternal black hole, which in the context of the boundary corresponds to the usual thermofield double state, as we know from Hahn's paper. So in this particular case, where we're considering the two-sided black hole, we actually have a pair of boundary algebras, AR. The subscript comma 0 will become clear later why I'm adding that. So a pair of algebras for the right and the left. And we also have a boundary Hamiltonian, HR, which is naively also a single trace operator, except it has an extra factor of n in it, so some integral but it has an extra factor of n out front, and this extra factor of n is annoying because if you now compute, say, so it has a 0 expectation value if we trace subtract, but if you consider fluctuations in this operator, these fluctuations blow up as we take n to infinity, so this operator HR minus its trace is not going to be in this algebra. Okay, so there's a more formal way to state this result, which is that this algebra here, and this one, is what we call a type 3 von Neumann algebra. And type 3 just means that this is an algebra where there's no well-defined notion of a trace. There's no trace, which means there's no way to define density matrices. This statement is something which you might be familiar with from the bulk context, where this is really just the statement that if I draw the picture for the two-sided black hole, this operator HR is dual to the one-sided boost generator in the bulk. So it's the guy that does this. And if you look at the action of this on bulk quantum states on some slice, what that does is it takes quantum states which are initially smooth on a slice and it maps them to singular states because it dephases one side compared to the other side. So if you try to like define a one-sided density matrix, it would just run amok.
Sorry, Ven, can you be a little more clear? So this HR, that integral is over the boundary or it's over
Yeah,
the bulk?
this is in the boundary. Yeah.
But then I wouldn't say that that's what this does in the bulk. I would say that's the ADM Hamiltonian, and you're perfectly allowed to go up and down with just one of the ADM Hamiltonians, because you can complete the slices in the bulk however you want.
Yeah, what I mean is if you try to think of this as no, but you would have to tell me what the other side does in order for that to be true, right?
Well,
you mean like including the constraints?
I can take HL to be 0. I can just not act with HL, right? I can just act with HR, and that's perfectly smooth in gravity. You're right that in quantum field theory in a fixed background, if you interpret this as a half Rindler boost, then it does what you said.
Yeah, but at n equals
that's not what it's equal to.
But at n equals infinity, the only thing that's going to happen in the bulk is the QFT. The QFT is going to move around, and gravity's not going to do anything, right?
No, I think the ADM Hamiltonian will act on the gravitons and so on too, right? I mean, it's just
No, but at n equals infinity, it's just like QFT on some fixed background, right? So it should just be boosting the QFT degrees.
I think you have some implicit choice of gauge in mind, right? I mean. Yeah, if it's right, that's right. I agree with one. Yeah, I agree.
I'm just trying to describe a bulk reason for the fact that you get type 3. Like on the boundary, it's related to the fact that this thing is just going to be infinite.
Roughly speaking, I would have said that what Juan called the bulk Hamiltonian, the Rindler thing, is equal to the ADM Hamiltonian plus some multiple of the area. And then if you act with the area, then it's really the area that's creating that singularity. It's not the ADM Hamiltonian.
Sure. Okay. Yeah, that's fair. Yeah, I think Monica had a. Sorry, I couldn't.
So even after all that logic, which was my first question, the second question is that why does that prove that it's type 3?
Why is it true that this is type 3? Yeah, I can give you a purely boundary explanation for it. So it's essentially because the Hamiltonian itself has an expectation value that goes like n squared, but typical excitations above the vacuum have order 1 energy. So in the n goes to infinity limit, you end up getting a continuous spectrum, and that is a telltale sign, and this thing corresponds to the modular Hamiltonian.
So you
of
mean
the DFD state?
particularly type 3-1 then?
Yeah, it's a type 3-1, exactly.
Okay.
Yeah, right.
Okay.
Isn't the more careful thing to say that there's a half-sided modular inclusion, so you know, at infinite n, so you know?
Yeah, I mean, I guess you could make,
that would make Monica happier. Yes.
You can say that the automorphism is always outer.
Yeah. Yeah.
There was
Which is really just a statement that this isn't in that algebra. Yeah.
There was another question somewhere?
Raphael had.
Oh.
You want me to add a 1 here? Yeah.
Someone else had a question there, or it's gone? Okay.
Okay. Okay. So all the words that we just said is really in the limit that n goes to infinity. But in the n goes to infinity limit, you're really doing QFT on a fixed background, and we want to understand back reaction of quantum fields and when gravity is really turned on. So what Edward did in his original paper was to consider a power series expansion in 1 over n, like we usually do. But if you're trying to do this algebraic formalism, that power series is not really a nice thing to consider, at the least because when you're trying to define von Neumann algebras over a power series, things get really complicated, and a lot of the results that mathematicians have worked out, it's not at all obvious that it carries over. But at an even worse thing is that when you're trying to define traces in this formalism, if you're doing things in a power series, you'll end up getting things like the trace will go like e to the n, and when you take n to infinity, the thing just blows up, and there's no way to define a power series expression for the trace, in which case the density matrices are not going to be easy to define. And so we don't really want to do that for our purposes, because we really want to understand the generalized entropy. So instead, what I'm going to do is consider a microcanonical thermal field double, where it'll become evident that we can get around having to do a power series. Things work out much nicer. Okay, so microcanonical TFD. I said TFD here, but I really mean microcanonical. Looks roughly like this. There's like a normalization factor out front that I'm not going to write down because it's not too relevant. Sorry. Okay, so it looks more or less like the usual TFD state, except there's this window function which is sharply peaked around some value E naught of the energy. And to be explicit, we can, for example, consider a window function which is a Gaussian. Sorry, sigma squared, where sigma is like the standard deviation. And this energy scales like n squared, as we just mentioned. So if you try to like do the saddle point approximation for this, and you want to figure out what state this is sharply peaked around, you can convince yourself that if you take the standard deviation, the fluctuation, to be order 1, you can get the saddle point approximation to work out, and you'll find that the energy, unsurprisingly, is E naught, plus. It deviates from this E naught energy by some order 1 amount. So you're in this like microcanonical energy window. And the nice thing about this state is if you now compute the fluctuation in the Hamiltonian, but in this state, then you'll find that, you'll find that the fluctuations are order 1 instead of order n squared. So what that essentially means is this operator, HR minus E naught, is perfectly fine in the limit that n goes to infinity. Okay, it doesn't blow up. It's a totally well-defined operator, finite correlation functions. Okay, yes.
Is this a fixed area state, or is that something else? Is this an example of one?
No, I don't think this is a fixed area state. To leading order,
Leading
sure.
order,
Yeah,
yes,
okay,
I think.
Yeah.
I mean, a related question is, does this state have a good geometric dual? I would have guessed no.
Well, Don Merolf had this paper where he tried to argue that in the semi-classical limit, it looks like it looks like an eternal black hole, except you can also take it to be very small, which you can't in the canonical case. But it's like essentially dual to an eternal black hole with a mass that's peaked around E naught.
I think he was thinking about small black holes, though. I guess if it's big,
I think that statement is true when sigma scales like an inverse power of G.
yeah, then I would be happy.
But
Then I
the
would be
value
happier,
of G,
yeah.
you can take the value of G such that like the coefficient is 0. I'm pretty sure you can do that. Like you can take it to the limit that it's order 1.
I mean, I thought about this state at some point, and I seem to remember that it seemed non-geometric in the sense that the length of the wormhole depended on the frequency of the perturbation, which is
Okay.
not a very geometric
Yeah.
thing. Yeah.
Okay.
Maybe it's okay, but
No. Yeah, no. That's a good point, and I will get back to we essentially restrict to a class of states in this setup where you don't get the non-geometric fluctuations that you're talking about. But it is like we restrict to a special class of like semi-classical states where there is a good bulk dual.
I mean, I guess we could also just say fixed area states are not semi-classical because the
Yeah.
metric is not coherent in a coherent state.
Right. But I will make that more precise. Yeah, Juan.
You can get these states by integrating over the time of the thermal field double.
Yeah.
So the semi-classical aspect is only in that time, right?
Yeah,
Right,
it's
right.
So
if
for
you
the bulk
consider.
observer, everything is perfect.
Yeah, yeah, and
That's
so
right, it's a superposition of a bunch of different thermodynamics.
exactly, yeah, yeah. So so we basically will restrict to a class of states where you're not allowed to consider like big superpositions. It's just like a tiny range around like whatever the like fixed time is.
All right, thanks.
I'll write that down and make it more precise. Yeah, but yeah, exactly. Okay. In order to move forward and get more insight into what's going on, it's helpful to consider the bulk dual of this picture. As n goes to infinity, so this thing is essentially going to correspond to an eternal black hole with some fluctuations on top of it. And as people just said, like you can get things which look like superpositions over different times. And I'll come back to like the restriction we make so that we don't consider non-semi-classical things like that. But at a very basic level, where this Hamiltonian is going to be dual. So, sorry, actually let me be more precise. Forget that statement for a second. In this geometry, wait, where did I? Okay, just for notational simplicity, I'm just going to call this psi. Okay, and in the bulk we have this modular operator delta psi, which is just e to the minus h psi, where h psi is the two-sided boost generator on this background that does this and also does this. Okay. So the fact that h psi, the modular operator of the state psi, does this action is this famous result by Bisignano and Wickman that is fairly concrete. For us, the relevant thing is if you look at the commutator between HR minus E naught and any operator in the right boundary algebra. So we know that this thing generates this action on operators in that algebra. And we know that in the bulk, partial T times beta, where beta is the inverse temperature, is just the boost generator. So we can identify HR minus E naught with the, as far as the right algebra is concerned, we can identify HR minus E naught with the boost generator up to an overall central term, a term which commutes with all the operators in the bulk algebra, or respectively the boundary algebra. Okay, and I'm going to just for notation, I'm going to distinguish the boundary algebra on the right from a bulk algebra in this wedge. I'll just call that little r, but they're dual to each other in the usual way. Okay, so this thing is equal to h psi plus an extra central term, which we can't get rid of because I'm identifying them via the commutators. Okay. Okay, so we want to understand the structure of the Qfd algebra plus what happens if we consider this extra operator, or the right-hand side. So what we can do is we can take the operators in the Qfd algebra and adjoin them with the action of this operator. So if we do that, we get something called a crossed product. Where this is the Qfd operators, and this is the algebra of bounded operators, which are functions of x plus h psi. And this symbol here is a cross product, and all that means is if I take any operator in this and I conjugate it by this operator, I'm going to get back an operator that's in this. But this thing itself is not in this algebra because it's the modular automorphism group. Because I've only identified this with this via their commutators, and in general, there can be an extra like term there that's purely central that I can't get rid of. Sorry? Sorry, I didn't hear what you.
It commutes to the left and the right.
Yes, yeah. It commutes with the left and the right, yeah. Okay.
Actually, let me also ask about that. So you said you wrote the words type 3.1 here, which I implicitly interpret as saying that the algebra is a factor.
Yeah, it's a type 3.1 factor, yeah.
But so then if it's factor, then what does central mean? There's nothing central, right?
This x is not in this algebra or anything. This x is an extra thing that I've just introduced. This type 3.1 is just the Qfd operators. That's a factor. So the x plus h is in this new algebra that I've just defined.
Which may have a center.
Well,
the idea, or-
if it just had x, it would have a center, but x plus h is not central. And so this thing is also a factor.
Okay.
Yeah.
But x is, when you say x is central, it's central in what algebra?
It commutes with any operator that's in this. In a r comma 0.
Oh.
So you're effectively doing like a similar thing from like a Lie algebra, you just have the additional automorphism group onto, so your type must have changed. There should be then type 2.
Sorry?
So your
it should be what?
So your new algebra, since
Yeah.
you now did the cross this product on top of the automorphism group,
Yeah.
so that should be then type 2, because that cannot be continuous anymore. Because
You-
your added center will be effectively discretizing, and that'll be type 2.
You're saying this should be type 2?
Yeah.
Yeah, that's
Oh,
right.
okay.
Yeah, that beat me to the punchline. As Monica said, this should be type
Spoilers.
2, and my talk is done. Right, that's right, exactly. Where was I? So, is there another question?
One
Yeah.
more thing. So are you picking a unique set of center there as like an X that
No,
commutes with L and R? Because that cannot be possible. So that's generically possible of many different sets.
Yeah, no, X is not unique.
So what are you picking as an X as a set here?
Just X is only defined up to the fact that you can shift it by some arbitrary constant. I'm not picking any particular X here. This is only defined up to the usual automorphism symmetry of the.
Okay, then are you
And
generating?
that will come in later. It'll be relevant later, what that additional ambiguity is. When I try to
then
define
you're
traces.
not fixing the Hilbert space of the you generate.
No, I'm not
Okay.
claiming to, yeah. Okay, so, so as Monica said, so there's a well-known result due to cons that if you take a type 3.1 algebra and you take its cross product with its modular automorphism group, it becomes a type 2 algebra. And in our particular case, as will become clear later, it actually ends up being a type 2 infinity algebra. So what does that mean? It'll become more explicit later, but all this means is it's an algebra where you can actually define a trace, but the trace is going to be infinite for some subset of the operators. In particular, the trace will be infinite for the identity operator, which is what this infinity means. It means the identity operator itself has an infinite trace. But there is an actual trace now. If you have a trace, you can then ask about things like density matrices and the entropy, which we couldn't do before. So it's one step better than what we had before. But I will make that more explicit. Okay. And then one last thing, in terms of the statements, is we can ask what if there's a GNS representation for this algebra. The Hilbert space, the GNS representation of this guy by itself just corresponds to the Hilbert space of perturbative excitations around the thermal field double. But it's a two-sided Hilbert space that you can't factorize it, of course. And that Hilbert space I'll call H naught, and it's essentially the span of operators acting on the Tfd. But now for this algebra, the associated Hilbert space looks like this, where this L2 of R corresponds to the wave functions of this variable x. Okay. So before I get into the explicit formulas and stuff, what's the physical picture here? Like, what's actually going on? Roughly speaking, what I'm about to say is not something that's precise, but it's just to give intuition. We can, roughly speaking, identify this x as essentially like the gravitational part of the ADM Hamiltonian. Normally, this is something that's treated classically, right? We think of the ADM energy of a black hole as some classical thing. But what we're going to do here is actually treat it as a quantum mechanical operator. We can consider wave functions of it and so on. And the conjugate to the ADM Hamiltonian is the boundary time shift. So here's the two-sided black hole again. Here's T right, T left. If I shoot out a geodesic from here and look at where it lands here, some T tilde R or whatever, this time difference is the canonical conjugate to this ADM Hamiltonian, and this is something which you can make very explicit in JT gravity. This was done by the two Daniels, Harlow and Jaffrus. And essentially the same it's essentially the same picture here. This L2 of R mode is a gravitational mode that corresponds to these boundary time shifts. Okay, so there's an X and a P. X is like the position operator, P is like the momentum operator, and they correspond to the Hamiltonian and these boundary time shifts. And so what's going on here is essentially we're taking the Qft degrees of freedom and we're augmenting it by what's essentially like a gravitational edge mode or a gravitational boundary mode that we can now treat as like an actual quantum operator if you were to do like canonical quantization. You can have an equivalent picture where instead of the ADM Hamiltonian and the boundary time shift, you can think about the area of the bifurcation surface and the boost angle. And those two pictures are completely equivalent. And in that case, this extra piece of the Hilbert space would correspond to quantizing the boost angle of the black hole. In particular, even if you don't have matter around, configurations with different boost angles are different quantum states now. Okay, so even if you don't have matter, just the different boost angles are different quantum states, and that's basically what this extra piece is here. Okay, and so our goal now is essentially to compute, so we can define a trace and we can define density matrices, and we want to know what is the entropy of states in this full algebra. Okay? All right. Any questions before? How much time do I have, by the way?
You've got, let's say, 15 minutes left plus questions.
Oh my God, okay. All right, I'm gonna have to rush through stuff. Okay, so if I consider an operator that's in this bigger algebra, AR, that we just defined, then a basis of such operators will look like an operator in the original algebra and times the adjoining by the modular flow and then this extra X piece. And we can consider a special state, which is just the, just write it down first. it's the original cyclic and separating state of our quantum field theory Hilbert space, which is the TFD state, or the Hartle-Hawking vacuum. And then we can then consider a state now in this H, which includes this L2 of R piece, so it's some wave function g of x times this basis. This state has a very nice property, which is that if you try to write down the modular operator for psi hat, you can show that it actually factorizes into an operator that's solely in this algebra AR times an operator that's solely in the complement of this algebra, which you cannot do for a type 3 algebra. The modular operator cannot be written as a left and a right part, but for this type 2 algebra, you can do this. Pratik, yeah. Is the what related? No. Just G is not related to the F. This is just this G is just some arbitrary wave function that lives in this L2 of R.
But doesn't the boundary wave function like fix what the distribution of x should be?
F would be. Sorry. No, you're right. For the TFD in particular, I was jumping ahead. Sorry. For the TFD in particular, this is the profile given by the F we picked earlier. But later, I'm going to consider other states on top of this, and then in that case, like the G could be something else.
So there's some unique, like there's some isometric map from the boundary Hilbert space to
Exactly.
this H.
Exactly.
Thanks.
Okay. So we say that so the words are that now delta is inner because, this is in AR. Okay. Now, one important thing is that this X is not uniquely defined, but you can always shift it by some number C. And as a result, you can show that this delta R itself is also not uniquely defined, but you can always rescale it by e to the minus C. And the reason that that's important is we can now go ahead and try to define a trace for this algebra. Right? And I'm just going to tell you the definition of the trace. I'm not going to show you where it comes from. But let's define the trace of any operator A in this algebra by the following formula. Okay. You can check that in the specific case of like the ordinary quantum mechanics, this is going to give you back what we usually think of as the trace. But the main point is that this definition of the trace is not unique. You can always rescale it by an overall, this e to the c that shows up there, what that means is essentially when we eventually define the von Neumann entropy, that entropy is not going to be unique. It's only going to be defined up to an additive constant. And that additive constant is essentially like an infinite renormalization factor for the generalized entropy. Hopefully I'll be able to get to that. Okay, so let me talk about density matrices really quickly. Oh wait, no, I already said what I wanted to say. Okay, so let's come back to this picture here. I'm going to focus on the bifurcation surface. And I'm going to restrict myself to what we call semi-classical states, which are states for which the fluctuation in the boundary time shift is small. So we're not going to consider large superpositions of different time shifts. Okay. So what that means is the fluctuation in the conjugate momentum, P, where x comma p is equal to I. The fluctuations in this thing, we're going to consider a special class of states where this is some small number epsilon. Okay? Where epsilon is some n-independent number that's much less than 1. So essentially, we're going to take n to infinity and then work perturbatively in this epsilon. And explicitly, a generic semi-classical state in the Hilbert space that we're interested in, which I'll call phi, to distinguish from the special state there, will take the following form. Where g is just some wave function, but now there's this epsilon. And my claim is that I can define a density operator associated to this phi hat, and the von Neumann entropy, a density operator in the algebra AR that we talked about earlier, the cross product algebra. And the von Neumann entropy of this density operator has an explicit formula that's given by this. And sorry. And in the time that remains, I'm going to just give you the interpretation of this expression, okay? But essentially it has a term that's just coming from x plus h, which is essentially like, remember it's like the ADM energy. It has a term, this thing is the relative modular operator, and this quantity here is essentially the relative entropy in algebraic Qfd. And then it has this extra term here, which is a correction term that we often don't talk about when we talk about black hole entropy, that's just coming from fluctuations in the time, or fluctuations in the energy, whichever way you want to look at it. So I'm not going to prove this for you because that's just some like technical proof and it's not going to provide any, it's not like insightful or anything. I'll just try to convince you how this is related to the generalized entropy. How much time do I have now?
Let's say 5 more minutes.
Oh, okay. Okay. Don't know how much. Okay. So let's ignore for a second that we're talking very specifically about type 2 algebras, type 3, blah, blah, blah. I'm going to pretend for a second that I can ignore all those issues and start talking about density matrices for the QFT, but it's really just to provide an interpretation for that thing over there. So the relative entropy of phi with respect to psi in algebraic QFT is just the expectation value of this relative modular operator. And if we were ignoring issues related to type 3, then this quantity is actually just equal to the right modular Hamiltonian expectation value, which is also usually called the boost energy, minus the difference in the von Neumann entropy of the reduced state for psi, and its difference from the reduced state for phi and psi, sorry. Okay. So the point is basically that that first term over there, the x plus h psi, remember that that's equal to the ADM Hamiltonian minus the energy of the thermal field double state. So it's going to be equal to the difference in the area between the unperturbed black hole and the perturbed black hole. So essentially the difference between the area at infinity and the original area of the black hole before we threw in the matter. So x plus h is essentially the change in the area.
So Ben, to be clear, are you somehow, like say in for example, in Aaron Wall's formalism,
Yeah.
that usually comes from solving the Einstein equation? Is that right? So you, because A shouldn't show up in terms of the quantum fields, right? So you should but you can have some integral involving the energy momentum tensor or something that you can then try to use Einstein equation to turn into an area. So is that where the area is coming here?
There is a step that does what that does, but this is a step before that, where all I'm using is that it's essentially like a first law. All I'm saying is the energy at infinity is equal to the area of the black hole at in the future limit. That's all I'm using
Well,
right
but
now.
why is that true? Probably because you saw
Well, it
the
is because of the Einstein
equation.
equations,
Yeah,
yes,
okay.
but yeah,
Yeah.
but, okay, yeah, it's because of the Einstein equations, definitely, yeah. Yeah, but the point is that you can show that the change in the area is, oh, wait, sorry. I think I might have skipped a step. Did I skip a step? Yeah, okay, so the point is you can show that the change in the area is equal to this thing over here, just using the Raychaudhuri equation on the black hole horizon, which is essentially what Aaron Wall did in his GSL paper. Sorry, did I? Yes, right. So you can basically replace this term here with the area difference, and then we have on top of that the entropy difference, and then we have that extra term, which is just the fluctuation entropy of the black hole coming from the energy fluctuation. So what we've basically shown is that the von Neumann entropy of the density matrix of this type 2 algebra, just using semi-classical Einstein equations on the horizon of the black hole, you can show that this is equal to the area of the perturbed black hole plus the entropy of the perturbed state plus a constant, which is just some arbitrary, it's just some state independent constant, which we can absorb into the additive ambiguity from the fact that we have a type 2 algebra. So the claim is that the von Neumann entropy of the type 2 algebra is equal to the generalized entropy of the perturbed black hole up to this state independent constant, which is essentially just an infinite renormalization constant associated to the vacuum state. Okay? So the punchline is essentially that using this formalism, we've been able to associate to the two-sided black hole and perturbations around the two-sided black hole a density matrix whose entropy gives you not just the bulk matter entropy, but also the area of the black hole. And it's essentially telling you that in this sort of hydrodynamic picture, the area of the black hole is essentially coming from this gravitational boundary mode or gravitational edge mode, whatever you want to call it. And in some sense, it's essentially like a continuum version of like Daniel's quantum error correction story, where we're doing like we're like the continuum in the sense of like quantum field theory with semi-classical gravity. And the point is that it's important that we allowed this gravitational edge mode to actually be some quantum mechanical degree of freedom in order to extract the actual area term from a density matrix. And I'll just quickly finish. So at least I feel that that's a very interesting result in and of itself. But what's also nice about this formalism is now you can ask, can we give an interpretation to the generalized entropy of other surfaces in the bulk? I anchored myself a bit to ADS-CFT here, but it really wasn't that relevant. And so you could just give me some, like, say, marginally trapped surface in the bulk, or even something simpler, like a non-minimal extremal surface, and ask, what is the interpretation of the generalized entropy of that thing? Can we find some operator algebra and some density matrix whose von Neumann entropy is that quantity? So this formalism lends itself naturally to that. You can then ask about things like, say, the quantum focusing conjecture from an algebraic QFT perspective, because then you can try to move beyond just like extremal surfaces. And I didn't have time, but if people are interested, I can talk about the de Sitter, like what happens when you try to apply this kind of formalism to de Sitter. But I'll just end there for now.
All right, so more questions. So maybe Monica, then Juan. Then, okay, lots of questions.
That was a great talk. And the one that you wrote right in the middle for the relative entropy, that's not unique to the type 2 cases. So why are you emphasizing this is only working for type 2, and why would it be not working for type 3-1? Because all you did is taking the definition of the relative entropy, which is just taking with the cyclic and separating state onto the log of the modular form, which is just true for any generic von Neumann factors.
You can
And
definitely.
you can decompose it like that for even one normal algebra of type 3. So I don't understand why that's so special about type 2.
So technically, I guess what I'm doing here is not kosher for type 2 or type 3 because you can't make this split. But you're right that this formula itself is like the definition of the relative entropy regardless of what the type of the algebra is. But the main point is that is not so much the fact that you can use this decomposition, it's the fact that if you combine this with the other terms there, you can actually reinterpret all of that as a density matrix in a type 2 algebra. So the generalized entropy could actually be reinterpreted as a density matrix. If you just gave me this formula, I wouldn't know how to do that in a type 3 algebra.
But that's generically based on how you pick that measure as the weight function, right? That G function is basically effectively how you mix that, and then that's like a measure that's given by your formalism for mixing as a directly as a this is how you added the automorphism group 4, right?
Depends on the measure. You mean like
Of that G.
the measure for the trace?
Yeah. But that measure was actually directly given by your function G as a weight function that mixes directly.
No. You can show that when you're actually computing the trace, the choice of G drops out completely. Like X is definitely going to be in the trace, but the choice of G will drop out in the actual expression for the trace. So there's a G independent measure that you end up getting for the trace. G here is coming, so the trace itself, the measure there doesn't care about G. The G here comes in, the G that's in the definition of phi hat just comes in here in the energy fluctuations of the black hole.
Okay.
Yeah.
Yeah, so if you didn't have the thermophile double, but some other state that has an RT surface,
That has a what, sir?
a Ruta-Kayanagi surface,
Yeah.
could you do something similar? Or, I mean, there you wouldn't have this ATM Hamiltonian, wouldn't be so obvious what that is. But.
I think every step goes through except for the very last derivation of trying to relate the von Neumann entropy to the generalized entropy, because there it's actually important that the modular Hamiltonian has a local form, like it's the integral of some stress tensor, in the like actual causal wedge, which is true in this kind of setting. But if you just gave me some arbitrary quantum extremal surface with some arbitrary state, then it's not at least true at the level of like strength that's true here, but it's possible that like you still be able to show something without needing something that's strong. For example, if you can prove there's something like a first law where like change in area is like the change in the boost energy, the change in the area is the change in like the modular operator for the state with that QES, then everything I think will go through the same way.
So I want to ask more about this comment about the other surfaces in the bulk.
Yeah.
So it seems like you need to have some interpretation of X. So
Yeah.
what are the rules? Am I meant to have an X for every surface, or what's the, yeah.
Yeah, I mean that's basically related to I think the answer I just gave to Juan's question, which is that in this case, X ends up getting an interpretation through the Raychaudhuri equation and the fact that the change in the area is related to the boost energy. X essentially gets an interpretation that way. For a more general surface, I don't have a great answer for how you would extract like systematically what the interpretation of X is, but I have a guess maybe for like some algorithm which might work, which is, so you can ask, like, I've talked about all this algebraic QFT stuff, but how is this related to the usual cutoff picture that we're usually used to talking about for the generalized entropy, where you introduce some sort of brick wall near the horizon. And in that picture, if you introduce a brick wall and you do QFT in curved spacetime, the brick wall is just some surface. But when you turn gravity on, that brick wall should really be like a dynamical boundary, and you'll get some extra boundary term there. And that extra boundary term, if you were to quantize it canonically, should, in that cutoff picture, correspond to what this X is. So if you just gave me a quantum extremal surface and I do this sort of brick wall plus dynamical gravity thing, it should be able to tell you how to like figure out what X is in the algebraic picture through the cutoff picture. But I don't have a great first principles way of figuring out purely from the algebraic language.
So if you consider an evaporating black hole and you distill the Hawking radiation into qubits,
Yeah.
then it seems clear that it's just type 1 from the point of view of the qubits, right?
Uh-huh.
Can you comment on that? Or?
Yeah. I mean, I think there you're really using the fact that you know something about the interior degrees of freedom. And in this picture, it's really more like a sort of hydrodynamic picture where you don't really know anything about the interior and you just know about this one like gravitational mode that's sort of living on the stretched horizon, which is the boost angle. So it's not smart enough to figure out that secretly there's really a type 1 algebra. It doesn't know about the microstates. And the thing you're talking about is really because we know at the end of the day there's like a finite Hilbert space with some black hole microstates. Is that?
I guess I just,
yeah.
Okay, I'll give up.
In other words, I don't think this would be able to see the fact that, like, in this picture, the entropy would just keep going up if you had an evaporating black hole. I don't think it would be able to see the fact that it really comes back down and you could actually, like, distill the Hawking radiation.
Can't you see other non-minimal, I mean, wasn't the discussion about non-minimal QESs and so forth? I thought any QES you were saying has some interpretation.
Yeah, but my guess is if you were to define the generalized entropy for other surfaces and you were to look at, like, say, the change in the generalized entropy as you move along the horizon of the entanglement wedge, you would, or sorry, along the quantum extremal surface as it evolves, it would just keep going up. Like, I don't think it would go back down using this formula. It just obeys the usual GSL, basically. Yeah.
Sorry, kind of a boring question. Where did you use the assumption that delta P is small in this claim?
It's in proving this formula.
Yeah,
There's really like...
Are there order epsilon
Yes,
terms that you don't?
exactly. I just didn't write it down, but yeah.
But what do they correspond to? I mean, what are they? It must have to do with fluctuations in the area, I guess.
Yeah, they correspond to corrections that come from the fact that the boost angle actually can fluctuate by an order 1
Yes,
amount.
right.
Thanks. Thanks, yeah. So actually part of my question was just asked by Adam. Basically, I was just going to ask you about the fact that you restricted your attention to these, semi-classical states where the time shift mode is not fluctuating much.
Yeah.
So I was wondering, maybe as another means of simplifying what you did, maybe you could consider allowing that time shift mode to have an arbitrary wave function, but taking the matter to be in the ground state. Do you think you could also get simplifications or an interesting entropy formula?
I see. Take the matter to be in the ground state, but you consider large fluctuation. Yeah, I think one situation in which it would be really interesting to consider that would be directly in, I don't know if we'd be able to get a handle on that in a very general case, but if you had JT plus matter, I think that would be an interesting thing to consider to see if you could actually get the Bekenstein-Hawking entropy when you could have arbitrary fluctuations in the boost angle. Because there, at least in pure JT, you can just directly quantize and there's no restriction on the fluctuations in the boost angle. You might hope that when you add matter, you can still make progress on that. Yeah, but I don't know, yeah.